78, we've got a concept question. We're asked to interpret what H prime 24 means. What's the best interpretation for this? Derivatives, of course, are instantaneous change. They're not an average, they're at a moment. And so if we've got temperature going on throughout the day, right? Big T and little t. Yeah, we're interested in what's happening at hour 24, right? We're interested in what's this change here, this slope or direction at hour 24. So it's not the change in temperature during the first day. It's clearly not A, and it's not during the 24th hour. It would be not during it, it would be at the end of the 24th hour or at hour 24. The average rate, it's not an average. It's not a rate at which temperature is changing the first day. It is the rate at which the temperature is changing at the end of the 24th hour. E is our answer here. That's what a derivative is. It's the, at that instant, at that particular moment, how is the change occurring? No calculator in that last one, but clearly a need for one in this one. We've got water flowing out of a tank. At time zero, the tank holds 81.637 gallons, and we know the rate at which water's flowing out. That rate is this one. We want to know how much flows out in the first 6 minutes between 0 and 6, and we want to subtract that away from what we started with. So we want to accumulate the water, the rate that flowed out, and let me kick a 9 up front and write sine square root of t plus 1 dt. So that's the integral that we need, and we need to take it to the calculator now, which I did already. I think it's down here. There she is. And see how it compares. So we put the numbers in. Of course, I wrote the 9 up front or the 9 on the inside. Doesn't really matter. The calculator says 36.606, and that's choice A. And that is the correct answer. 80 is a concept question again, and it's talking about Riemann sums and whether or not we have overestimates or underestimates. Specifically, we're interested in which will result in underestimates. So keep it simple. Think about left Riemann sums. Let's say we just had 2, and we drew them in from the left, and we made a calculation, and clearly we would have an underestimate if we used a left-hand sum. If, on the other hand, we did just 2 again, but we did a right-hand sum, think about how that would differ. If we used a right-hand sum, we'd be taking our measurements over on the right, and we'd form 2 rectangles this way, and clearly we would have an overestimate with a right-hand sum. Finally, with a trapezoidal, with an increasing function that is concave down, what would that look like? Well, think about that guy. If we drew in just 2 trapezoids, notice that, and I'm exaggerating a little bit, but clearly they would underestimate the area under the curve. They do better than either left or right, but we'd clearly have underestimates. So which gives us underestimates? It would be numbers 1 and 3. Letter D is our answer for number 80. Number 81 would, the easiest way to do it is with the calculator. And I've gone off and I've made a sketch of the first derivative. This is a graph of the first derivative. It is not the function. It's the first derivative graph. And they want to know how many points of inflection does the graph have. Well, from this first derivative graph, I can come up with the second derivative graph. I can see that, well, geez, I'd have a direction of 0 here, roughly about there, and then, here's a minimum point. There'd be another 0 there, and yet another here, and finally one there. And then my concavity in these moments, or my second derivative, excuse me, it's increasing, so it'd be positive, then it would decrease until I got to this moment here at the bottom. It'd be decreasing, so it'd be a negative derivative, and then it would be positive, and then negative, and then positive again. And they say, okay, now using this second derivative, or the implication here is using the second derivative, thinking about it, how many inflection points would there be? Well, inflection points are places where it changes concavity. So the function goes from concave up to concave down. There's 1. From concave down to concave up, there's 2, that moment there, right? At this moment here, we'd have a third inflection point where it went from concave up to concave down. And finally, we'd have a fourth one here where it went from concave down to concave up. So 4 is our answer. B is the guy for number 81. 82 is a concept question again. And they're saying we've got a continuous function between A and B. Which of the following must be true? Well, it says there must be a number C such that f of C equals 0. A C between A and B. Well, I can clearly think of the possibility that that might be true, but it doesn't have to be true. I mean, here's A and B drawn for A as a possibility, and it never goes to 0 at any point between A and B. So A is totally false. It doesn't have to be true. Part B says there's a number C in the interval such that C is between A and B. F of C is between A and B. Well, I can think of a number, F of A and F of B, that they give the same result. And C would not, there wouldn't be any value between A and B that would be between A and B because A and B are the same number. So I can think of situations where this is not true, so it's not a must. So that's a false. In C, letter C, it says there's a number C in the interval such that f of C is greater than f of x for all x's in the interval. Well, again, that doesn't need to be true. F of C, it implies that there has to be a max, and there doesn't have to be a max in that interval. It could be a situation like this, where all C's between A and B are less than. It's not a must statement again. It could be, but it's not necessarily true. D says there's a number in the interval such that its derivative is equal to 0. That implies that there has to be a max or a min. But again, we can easily illustrate something like this, where there's no C between where the derivative is equal to 0. All the derivatives are constant here, maybe a -1 or so in my example. So this is another false. So we're running out of possibilities here. It better be D. It says there's a number in this interval A to B such that the derivative of C is equal to the so-called difference quotient. Well, if f of A and f of B are here and there, that difference quotient is displayed by this slope, f of B minus f of A over A minus B. we know that no matter how we draw a continuous function between these two, there will be a moment in there somewhere where it's going to have that slope. At least one, could be more than one. This is a direct implication of the mean value theorem. If you don't know your mean value theorem, this is the direct implication. This is how that theorem reads. So E is the answer to 82.